My name is Matheus dos Santos. I am a PhD student at Centro Brasileiro de Pesquisas Físicas. My advisor is Sérgio Duarte. My project is named Neutrino Physics and their process nucleosynthesis. In nuclear astrophysics, the rapid neutron capture, also known as process, is a set of nuclear reactions that is responsible for the creation of approximately half of the nuclei having the iron. So their process usually synthesize the most neutron-rich stable isotopes. Their process must occur in a region where high density of free neutrons is present. The process is believed to operate very close to the neutron dip line. That sits far away from the bad stability line, as you can see here in this picture. So the most probable candidates sites of the process occur is the core collapse supernova and the neutron star merging. These two sites can provide the perfect conditions for the air process occur. So to study their process, we use the Gross theory for beta decay. This theory permits us to evaluate the half-lives of beta decay. We will need to evaluate the total rate for allowed transition. That is Fermi-Gamow-Teller. As you can see here in equation 1, the total rate is a function of the nuclear matrix elements of Fermi and Gamow-Teller transition. So this total rate capture have a term here that is the k-value. That's the difference between the mass of the daughter and the father nuclei, as a function also of the Fermi integral, as you can see here in equation 2. The energy of the beta transition is given by this equation here. So the k-value is the difference between neutron atomic mass of valent daughter nuclei, as you can see here in equation 3. The squares of the Fermi and Gamow-Teller matrix elements are determined by equation 4. That's it. This nuclear matrix element is a function of the state density, as you can see here in equation 5, and the energy distribution that measures the probability that a nucleon with a single particle energy undergoes by a beta transition. This distribution can be a Gaussian-like distribution, as you can see here in equation 6, or a Lorentzian type function, as you can see here in equation 7. So the resonance energy can be evaluated by equation 8 and 9. Equation 9 was first proposed by Takahashi Yamada in the original work, but in this work we will use the equation 10 for evaluate the Gamow-Teller resonance. So in this work we use a large number of nuclei. So it's necessary to calculate the standard deviation and use the chi-square minimization, as you can see in equation 11, where sigma n is a adjustable parameter, and the chi-square minimization equation 12 and 13. So we will calculate the neutrino capture, as you can see here in this equation. For calculate this capture, we will need to evaluate the folded cross-section. That's a function of the Fermi-Dirac distribution. So this Fermi-Dirac distribution, we use zero chemical potential. This distribution is a function of the neutrino energy and the neutrino temperature. So the neutrino cross-section can be written by equation 16. as you can see here. So we will need to evaluate the dispersation to calculate the all to calculate our neutrino capture. So that's it. Thank you.